Hello students, welcome to the fifth video on maximum likelihood estimate. So this may be a little bit repetitive, but I wanted to cover this concept of maximum likelihood estimate with help of one specific example and demonstrate it on real data. So we will demonstrate the concept of likelihood on real data, and here real data is quote unquote toy data because I would be assuming one x vector. So let us say that we have an x vector which is equal to 2, 2.5 and 3, and we want to compute the likelihood of x vector. If we assume the following cases, in first case we assume that mean is equal to 2 and variance is equal to 1, and in second case we assume mean is equal to 4 and variance is equal to 2, and we didn't want to calculate, given that this mean is equal to 2 and variance equal to 1, what is the likelihood of observing x vector. And in second case, let us say that our observations are coming from a normal distribution with mean equal to 2 and variance equal to 1, and in second case it is coming from a normal distribution with mean equal to 4 and variance equal to 2, and we want to compute the respective likelihoods. So here again, going by the assumption of IIDs, what we can say is that f of x equal to 2, if x is our random variable, times f of x equal to 2.5 times f of x equal to 3. It can be written as, if x is coming from normal distribution, as 1 upon root 2 pi sigma square e raised to power minus x minus mu whole square upon 2 sigma square. And here, since we have three values of x, xi would vary from 1 to 3. Now all we have to do is plug the value of sigma square and mu for two cases. Hence for case A we can write these expansion as 1 upon root 2 pi 1, because sigma square is 1, e raised to power 2 minus 2 square upon 2 into 1, because again sigma is equal to 1, multiplied by 1 upon root 2 pi 1 e to the power minus 2.5 minus 2 square upon 2 into 1. Remember, this is e raised to power into 1 upon root 2 pi 1 e raised to power 3 minus 2 square upon 2 times 1. And this implies that likelihood of observing x. So when we generally say that likelihood, we always write the parameters first. Likelihood of theta given x equal to 2, 2.5 and 3, which is as good as saying that we are calculating the probability of observing x vector given theta, can be written as, and here also theta is a vector because we have two unknown quantities to be estimated. This likelihood can be written as 0.39 multiplied by 0.35 multiplied by 0.24. Just by solving 1, 2 and 3, we get this as 0.0376. Now, if this is the likelihood of observing x equal x vector given 2 and 1, we can do the similar math for case B, where we are interested to calculate the likelihood given that mean is equal to 4, variance equal to 2 for same x vector, and in that case we have to solve 1 upon root 2 pi 2 e raised to power minus 2 minus 4 square upon 2 into 2 multiplied by 1 upon 2 pi 2 e raised to power 2.5 minus 4 square upon 2 into 2 multiplied by 1 upon root 2 pi 2 e raised to power 3 minus 4 square upon 2 into 2. Now if you clearly see here that we are not doing nothing special, again we are just substituting values and we get the value of 0.00336 after solving this particular expression. Now, how to infer these two values? So in first case, we got the values as 0.0376. In second case, we got the value as 0.00336. So if we have to make a choice between mean equal to 2 and variance equal to 1 versus mean equal to 4 versus variance equal to 2, I would go with the first option, because likelihood of observing x vector for that particular mean and sigma square is higher than the second case. Now, if this concept is clear to you, in last video we also talked about optimization, that is that how many options are we going to check, that is going to be practically infeasible. Hence we identify the stable points, that is where slope is equal to 0, and based on that we differentiate the log of likelihood for mathematical convenience and equate it to 0 by differentiating it with respect to mean first and secondly with respect to variance, and whatever solution we get, that should be our answer. So I have a question for you before we move to next direction. So here are the two questions that once you solve, please put your answer into the comment section and I will let you know whether your solution is right and wrong. So question is, can you calculate the optimal value of mean and sigma square for x vector equal to 2, 2.5, 3, where you can assume that x is following a normal distribution with given mean, with unknown mean and some variance that we have to determine. Once you are done with this, we will move to applied aspect of likelihood, where we will discuss linear regression problem as the problem of maximum likelihood estimate, understand AIC and BIC for model selection criteria, and we will also learn something about extreme value theory, which holds a special place in earth and environmental sciences, that how log likelihood can be used to understand and study extremes where random variables do not follow the normal distribution.